Uh, Hello, my name is Jose Morales and I will be presenting a multimodal approach to the detection of web-based attacks, a summary. The name of my teammates are Jonathan Sotelo and Richie Gonzalez. So, here we go. Uh, Well, as I said, this is a summary. All the credit of the investigation and the actual paper goes to these guys, Christopher Krugel, William Horstan, and Giovanni Vigna. So, background. Web servers and web-based applications are being attacked frequently. To detect web-based attacks, intrusion detection systems (IDSS) are defined with several signatures that support the detection of known attacks. Unfortunately, it is hard to keep intrusion detection signature sets up to date with respect to all of the continuously discovered vulnerabilities. To overcome these issues, misuse detection systems should be complemented by anomaly detection systems, which support the detection of new attacks. In addition, anomaly detection systems can be trained to detect attacks against custom developed web-based applications. The paper presents an anomaly detection system that detects web-based attacks using a number of different techniques, which we will be seeing later on. Intrusion detection. Anomaly detection that relies on models of the intended behavior of users and applications and interprets deviations from this normal behavior as evidence of malicious activity. The difference can be expressed either quantitatively or qualitatively. The, the classification of intrusion detection approaches into anomaly-based and misuse-based is orthogonal with respect to the particular technique used to characterize normal or malicious actions. Methods for finding expected behavior, signatures or policies when these are broken, or statistical analysis. Learning-based anomaly detection. It refers to the class of approaches that rely on training data to build profiles of the normal benign behavior of users and applications. Techniques: data mining, statistical analysis to characterize user behavior. Other types Other type of classes focus on the characteristics of specific applications and the protocols they use. These application-specific profiles are then used to identify attacks that produce previously unseen sequences. Approach of the ethers. It has two primary focuses: the quantity of different models to characterize the parameters used in the invocation of the server-side programs. By using several models, it is possible to reduce the vulnerability of the detection process with respect to mimicry attacks. The models target specific types of applications and, therefore, they allow for more focused analysis of the data transferred between the client, the attacker, and the server-side program, the victim. The goal of the system proposed is to perform supervised learning-based anomaly detection. It can be deployed on a host that contains custom-developed server-side programs and automatically derive models of the normal invocation of such programs. The data model. The anomaly detection approach analyzes the HTTP requests as logged by most common web servers. The analysis focuses on requests that use parameters to pass values to server-side programs or active documents. The analysis process focuses on the association between programs, parameters, and their values. Detection models. The anomaly detection process uses a number of different models to identify anomalous entries within a set of input requests associated with a program. A model is a set of procedures used to evaluate a certain feature of a query. The task of a model is to assign a probability value to either a query as a whole or one of the query's attributes. Based on the model outputs, a query is either reported as a potential attack or as normal. This decision is reached by calculating a number of anomaly scores, one for the query itself and one for each attribute. The anomaly score for a query is derived from the probability values returned by the models that are associated with the query. A model can operate in one of two modes, training or detection. The training phase is required to determine the characteristics of normal events and to establish anomaly thresholds to distinguish between regular and anomalous inputs. The detection phase, anomaly scores are calculated and anomalous requests are reported. So here we have the algorithms that analyze features for detecting malicious activity. According to their approach to the problem, well, the first one is attribute length. The length of a query attribute can be used to detect anomalous requests, especially when the parameters are either fixed size tokens or short strings derived from human input. The goal of this model is to approximate the actual but unknown distribution of the parameter length and detect instances that significantly deviate from certain normal behavior. For an example will be like a huge name of an attribute. If the application is defined to have fixed size attributes containing a large one will be classified as anomalous. Number 2, attribute character distribution. The attribute character distribution model captures the concept of a normal or regular query parameter by looking at its character distribution. Attributes possess a regular structure, are mostly human readable, and almost always contain only printable characters. In case of attacks that send binary data, a completely different character distribution is observed. There are similarities between the character frequencies of query parameters. For an attribute of a legitimate query, one can expect that the relative frequencies slowly decrease in value. In case of malicious input, however, the frequencies often drop extremely fast. So this method will detect if there are weird characters in the attribute name. For example, a new line or a tab character. These are like really weird characters to have in a attribute name. Then we have the third one, structural inference. Often the manifestation of an exploit is immediately visible in query attributes, as usually long parameters or parameters that contain repetitions of non-printable characters. There are situations, however, when an attacker is able to craft their attack in a manner that makes its manifestation appear more regular. This model is useful for detecting all kinds of attacks that require the parameter string to have a different structure than a regular query arguments. Depending on the structure of regular arguments, it can also identify attacks that exploit errors in the program logic. So an example will be a cross-site scripting attacks where the end user or attacker introduces something like an HTML script, and the web application ends up executing that script when rendering the HTML. Number 4, token finder. The purpose of said model is to determine whether the values of a certain query attribute are drawn from a limited set of possible alternatives. When a malicious user attempts to use these attributes to pass illegal values to the application, the attack can be detected. However, when non-enumeration can be identified, it is assumed that the attribute values are random and no attacks can be detected by this model. An example would be when a select from a form in HTML is modified, like you to inspect element on Google Chrome and edit the values available in the select. Of course, that will be an illegal value and can be found on the server side part of the application. Number 5, attribute presence or absence. Most of the times, client-side programs, scripts, or HTML forms pre-process the data and transform it into suitable requests. This processing step usually results in a high regularity in the number, name, and order of parameters. Therefore, little attention is paid to the order or completeness of the parameters. The analysis is performed by this model takes advantage of this fact and detects requests that deviate from the way parameters are presented by legitimate client-side scripts or programs. The algorithm assumes that the absence or a normal presence of one or more parameters in a query might indicate malicious behavior, thus allowing for the detection of attacks where server-side applications are approved or exploited by sending incomplete or malformed requests. Well, an example would be the hidden attributes in requests, where most of the times our IDs uh, are saved so that the post request can be executed with certain ID. But when this attribute is modified, it can be detected and corrected. Then we have the attribute order, which is number 6. Program logic is usually sequential, and therefore the relative order of attributes is preserved even when parameters are omitted in certain queries. This is not the case for handcrafted requests, as the order chosen by a human can be arbitrary and has no influence on the execution of the program. The test for parameter order in a query determines whether the given order of attributes is consistent with the model. So this one is pretty self-explanatory. The attacker can define the parameters in the URL of the browser, the navigation bar of the browser, and define certain parameters in certain order. So the developers of the application have the possibility to define the structure of the parameters that are going to be sent to, let's say, a get method or post method. And then we have the number 7, access frequency. Different server-side applications are invoked with different frequencies, but the general access patterns for these applications remain relatively constant for a certain website. The goal of the access frequency model is to capture these access patterns. One feature of an access pattern sequence is the frequency of program invocations. The frequency of the application being accessed from a certain client, the total frequency of all accesses. Changes in access patterns can indicate attacks. So frequency. This refers when, uh, uh, according to the structure of the web application, you access more uh, certain pages more than others. Like you can you usually um, access uh, more the homepage of the application more than the let's say uh, than consuming some of the web services of the application as an example. Then we have number 8, entry request time delay. And normal client access patterns are often assigned that web servers or web application are the target of surveillance or attack by malicious clients. This model attempts to detect deviations from unexpected distribution of time delays for each protected web application to detect script or probes or attacks. For example, a bot continuously or trying to access the application at a certain date and time, uh, uh, and it stays there constantly trying to access again and again and again. So yeah. Number 9, invocation order. Web-based applications are often composed of a set of server-side programs which together implement the application functionality. The nature of a web-based application may impose a well-defined ordering over the invocation of its component programs. This model captures the order of invocation of web-based applications for a certain client. What defines this model the most is that it analyzes the structure of a sequence of queries instead of the syntax of the parameters of a simple query. The model can be used to detect attacks against the application logic. An example of this model, well, an attack to this model will be the login of a web application. You can access the homepage or certain features of the web application without first being actually logged in. So, in conclusion, there is no doubt that web applications and servers will be attacked in the future. Therefore, we need to improve the security of systems by meticulous processes like the ones seen in this paper. The solution proposed on this paper seems really complete. The authors have specified crucial processes for attacking detection like parameter checking, data analysis, character distribution, among others. So this is it. This is the reference, the name of the paper, and the APA citation. Thanks for watching. Uh, and that's all. Bye.